Welcome to the Confused Coder series. I am going to be making videos going over how to solve some interesting coding problems. So following up from the last video, we have the question that if you're given an array of numbers or integers, as in these two cases, you want to figure out if two of these numbers within this list of numbers, equals to a specific sum. So in this case, if you have the list 2, 4, 3, 8, and you're trying to get the target of 5, this would return true, and it would return true because you have the number 2 here and the number 3 here. So 2 plus 3 is 5, so you return true. Let's look at this example down here. In this example, we have 2, 3, -1, 4, and the target is 8. And in this case, we cannot find two numbers here such that adding both of them together would give us 8, so we return false. So there's a few ways we can approach this. So one thing to notice here is that it's not constrained to just positive numbers, or so you might have negative numbers within your input. Right, you can have even repeats, so I haven't specifically stated it here, but so we could have something like 2, like instead of this 4, we could have a 2, sorry, I got 2 up here, so 2, 2, 3, so 2 plus 3 equals 5, and this 2 plus 3 equals 5, so in both of these cases, we're just looking for one pair, so in this case we would have 2 pairs, so it doesn't matter, but well, the important thing to do, important thing to know is that there might be duplicates. So if you were actually asked this question in an actual interview setting, these are some of the things to ask because your algorithm or the way you're approaching the problem could change based on what you ask and what the response the interviewer gives. So let's think about how we can solve this, right, in the most naive way, or let's run through some potential solutions, right? So given you have this list, right, the most kind of naive way would be you would take each number and try to see if that number plus every other number within the list equals the target sum of 5, in this case 5. So you would say, you start at this 2, you would say, would 2 plus 2, does that equal 5? No. Does 2 plus 3 equal 5? Yes. Well, in this case, it's, as soon as you get a yes, you would just return true. So that's one approach, right? So you might ask, what is the runtime, or how do we analyze this approach, right? The point isn't just to give an answer, it's to look at the trade-offs and then decide what's the best answer in terms of time complexity and space complexity, right? So in this case, if we follow this approach of taking each number, comparing and adding every other number to it, seeing if you get the sum, what would be the runtime of this, right? So if you have a list of n elements in this, like if n elements in your array, the runtime of this would actually be O of n squared, because you're taking each element and doing essentially n-1 comparisons. So not comparisons, but like operations to do the checking. So you would do n-1 comparisons for this 2, n-1 comparisons for this 2, for this 3, this 8, so on and so forth. So it would be O of n. So in terms of time, it would be O of n squared for the time, and it would be O of 1 for space, right? Because it would be O of 1 for space because we're not using any other extraneous space. So that's one solution, right? So let's think about what else we can do. So instead of just doing that approach, what we could do is we could say, let's say we sort these numbers, right? So right now, this is not the best example, but let's go to this one. We could actually sort these numbers. So after we sort them, right? So let's run this on this example because it's more indicative of what we might be seeing. So if we were to sort this, right, we would have something like we would have -1, let's see, 2, 3, and then I believe a 4, right? So now the array is sorted. What we can do now is that we could say let's sort it, and then let's, for each element, let's say we start with a -1, we find the complement of it, right? So it's -1, and we're looking for, in this case, well, let's look at the 2, so and it's easier to think about it. So with the 2, you would be looking for a 6. Because the array is sorted now, you could do binary search and then just look for the 6, right? So what would be the runtime of this algorithm, right? So if we did this, sorting would be O of n log n, again, where n is the number of elements. So if we go back, we would say O of n log n, this would be to sort, right? And then you would actually have to do O, and then search for complement. So in this case, it would be O of n log n to sort, and then to search. Space-wise, we can say it's O of 1 space if you use something like quicksort. That's a fine assumption to have, because it's O of n log n on average on quicksort, so we have that. So this solution, so we've gone from O of n squared time to O of n log n time, which is, so between these two, we would say that this one is faster, right? So now what we're doing is that we're not actually, so we have constant space, so even in this solution, we can say it's O of 1 space, right? And what we can do now is look at, let's try to reduce the time complexity. So let's try to cut this down a little bit more. And one way we can do that actually is to look at the space complexity. So right now we're not using any space. So what we'll do is that we'll actually, to get a speed up in the time, we're gonna actually sacrifice our space complexity. So what that means is that we're gonna use more space, but we're gonna have a faster time. So depending on the situation, or if you're looking for faster time, that's one trade-off you can make. So let's see how that would work. So if we do it that way, right, what we would have to do is we have the same problem. So you have you have a bunch of numbers like 1, 2, 6, 3, let's say you have like -5, just to have some negative numbers in there. You could also have 0, which again, that's a valid assumption. So you have something like this, right? So what we can actually do is that the first thing we should do, as we're iterating through the array, what we can actually do is keep adding elements to your, some sort of a set or a hash set. So that way, what you would do essentially is say, let's say you add 1, you're at the index 1 at this. So in this case, if our target was, let's say it was 8, right? So if it was 8, the approach would be you iterate one by one, and what you're essentially doing is that before you add an element to your hash set, you check if its complement is within the hash set. If it is, that means you found a target pair, and you found a pair of numbers that add up to 8 or whatever the target is, and you can just return true. So iterating through this, how it would look right is that you would say, let's start at 1. So 8 minus 1 is 7. Do we have 7 in our hash set? No, right? So beginning, we have our hash set is it's empty, right? So we would add 1. So if we denote the hash set as h, we would say h equals, let's say it just has 1 in it, because we would add 1. So now we're at 2. So we were here, and now we come over here, we're at 2. At 2, we would say the same thing. Do we have 6? We do not. So we would say, now iterating again, we would say h equals 1 and 2. Okay. Then you iterate once again. And then at this point, you're at 6. And now you do 8 minus 6 is 2. We do a lookup of a 2, and we do have a 2, so we just return true. So as you can see, by sacrificing some of the space the space complexity, so asking for more space, we actually reduced our time. So the analysis of this approach would be O of n for time and O of n for space, right? And now we might ask, how can we do better than O of n time? And my answer to that is we cannot, because if you're and there's a good way to think about it, is that you have to look at each element. You have to at least do one pass through all the elements, because if you're only looking at half of them, you might not find the pair that you're like you might not find one of the numbers that's part of the pair that gives you the answer. So that's one way to think about how can we lower bound each of these complexities, because that gives us an indication of should we try to optimize further, or is what we have correct. So yeah, I hope that was helpful. So that was a run through of how you might approach a problem like this, how you can think about in terms of solving it. Yeah, so thank you.